Okay, let me spend just a minute going over the calendar. So this week we're just working on chapter P, which is pre-calculus topics. So these are all things that you've seen before over the past couple of years. We're not going to have a test over chapter P, but we're just going to do homework and review and start limits next week. So there's going to be assignments from each of the three sections in chapter P. I'm going to give you time to begin each of the assignments each day. Normally, I check homework every day, but I'm just going to group these three assignments together, and I'll check all three assignments next Monday. Okay. But I'll give you guys a chance to start each assignment from middle of class to the end of class. Okay. In your packet, you have I numbered each of the pages. And I want you guys to flip towards the back here. So I'm going to try to do this, because of the fact that not letting you guys hang on to your phones. Normally, I would ask you to just pull up the assignment page from the online textbook and work out the problems. But I'm going to try to print out each of the exercise pages so that if there's any time at the end of the class to do homework, you'll be able to have the problem directly in front of you. So this is page 8 and 9, and then P2 pages 16 and 17. Okay, and then P3 page 27 to 29. Okay. And also at the end, I included the solutions. Okay. Yes, question. Oh, yes, question. Yeah, right. Yes. Oh, and also, if you have your Who I Am sheet, you can turn that in to me as well if you haven't done so already. All right. So at the end, you're going to see the answers for the problems that I assigned. I'm also going to show you on the website where to pull the full solutions if you were working on it at home. Okay, but we're going to start off with notes. Okay, so first thing, finding intercepts. So x and y intercepts, these are locations where the graph crosses the x or the y axis. I'm just going to draw a visual here. Let's say I had graph. If I want to find the x-intercepts, those will be the locations where the graph crosses the x-axis or intersects the x-axis. I'll highlight that in red. The way I find x-intercepts is I replace the the y value with 0. Then I solve for x. When I solve for x, I'm able to find these physical locations on the graph. I want to find the y-intercepts, and I'm only given the equation. What I can do, if there's a y-intercept that exists, I would replace the x with 0 because the y-axis is where the x value is 0. And then I would solve for y. When I solve for y, I can pinpoint where that y-intercept is on the graph. We'll do some of this practice on the next page. Okay, the next thing, finding or determining whether our graph has any symmetry. So there's three symmetries that we're going to review. There's the y-axis symmetry, x-axis symmetry, and origin symmetry. So y-axis symmetry is a graph that looks like this, where you can imagine folding your graph across the y-axis and having the graph perfectly overlap each other. Okay, this will be an example of y-axis symmetry. We can tell by looking at a graph whether there's y-axis symmetry, but algebraically, the way we can tell if we're just looking at the equation, we can do this. We can replace every x in the equation with a negative x and see if we can clean it up or see if that negative x will disappear and if it can go back to our starting version. Okay, if we can work our way back to the original form, then we know that there is y-axis symmetry. Okay, we'll look at some examples. X-axis symmetry would be a graph that will look something like this, where you can imagine folding the graph across the x-axis and then visually able to get the graphs to overlap each other. Okay. X-axis symmetry, the way that algebraically we can prove that is true for the graph, we will take every y in the equation, replace it with negative y, and see if after cleaning up that negative goes away and if it goes back to the original version of the equation. Finally, there is origin symmetry. So origin symmetry will be something like y equals x cubed. If I can replace every x and every y with a negative x and negative y, and if I can clean that up and get it back to the original equation unchanged, then we're dealing with origin symmetry. Right. Visually, the way you can tell whether you have origin symmetry is if you can flip the graph upside down and convince yourself that visually nothing has changed. So here I'm taking another version of the notes and I'm flipping the graph upside down, and you can see the graph looks the same, even if when it's flipped upside down. Question here, can graphs with x-axis symmetry be functions? No, right? And the reason why is because this is an example of an x-axis symmetry. If I were to draw a vertical line, I'm hitting more than one point, right? That's the vertical line test. Vertical line test says if I drop a vertical line and if it hits more than one point at any point on the graph, I'm dealing with something that is not quite a function. Okay, example one. Describe the symmetry of the following. Y equals x squared. This is a parabola, so therefore this has y-axis symmetry. Okay. We can tell visually that a parabola this parabola has y-axis symmetry, but we're also going to prove this algebraically. So we're going to take our equation, replace every x with negative x, and see if we can make it go back to the original version. Okay, so I'm going to take the x, replace it with negative x. So if I try to clean that up, it's not going to take me back to the original equation. Yes, all right, so negative x squared. If I square a negative, negative goes away. So this does fulfill that x-axis symmetry test. Okay, y equals x cubed. Any guess what this could be? Thanks. Yeah, this origin symmetry. So y equals x cubed, that's this graph. This is what the y equals x cubed looks like. So origin symmetry is we can replace every x and every y with negative x and negative y and see if we can revert back to, we can algebraically get it back to our starting point. So origin symmetry. I'll replace the y with negative y. I'll replace the x with negative x. Negative y stays negative y. Negative x cubed, is that going to stay negative or turn positive? Negative. So I have two negatives here. Can I, what can I do with these two negatives? Yeah, if I divide by -1, I should be able to make it go back to the starting point, right? So I'm divide both sides by -1. Two negatives from both sides will just go away. So I'm able to make my way back to my starting point. And that shows I can confirm that we're dealing with an equation that has origin symmetry. Okay, y equals x squared minus x. Let's see here. If I replace every x with negative x, am I able to get back to my starting point? No, right? This x squared will go back to a positive, but this x will turn into a negative, and that's not going to, there's nothing I can do to make it go match the condition for y-axis symmetry. Okay. What about x-axis symmetry? If I replace the y with negative y, am I able to get back to my starting point? I can't, right? If I replace y with negative y, no matter what I do, if I try to distribute the negative through and change that negative to a positive, both of these terms will change to a sign, so it's not going to quite match up. Okay, so the last option. What about origin symmetry? If I replace every x with negative, sorry, if I replace every y with negative y and every x with negative x, so I just took every variable and replaced them with the negative version of itself. I'm just going to clean this up. Negative x squared becomes x squared. The two negatives become positive. Is this ever going to look the same? Right. If I distribute the negative through, I'm still stuck with something that doesn't quite match up exactly. There's a fourth category. What's that?
Symmetry.
No symmetry, right? So it's close, but it's not going to fulfill any of three conditions. So here, there's no symmetry. All right, we tested all three variations, and we can't get any of them to work out. Now, this is a parabola, but it's a parabola that's going to be shifted a little bit to the right. So that parabola is not going to allow for symmetry where if you fold the graph or the y-axis, it's not going to quite perfectly line up like you would expect from something with y-axis symmetry. Okay, let's look at the last option here, last example here. X squared plus y squared equals 25. Let's go through each of the tests here. If I replace every x with negative x, am I able to get back to my starting point? Yes, because these are all nicely squared, so the negative will go away nicely, and I'm back to my starting point. So this has x-axis symmetry. Sorry, y-axis symmetry. What if I tested x-axis symmetry and replace the y with negative y? Yes. Yeah, it will have it as well, right? If I replace y with negative y, it'll go back to y squared, and I can go back to my original equation. Okay, so this has x-axis symmetry as well. What about origin symmetry?
Yes.
Okay. If I replace both the x and the y with negative x, negative y, they will both revert back to the starting equations because the negatives will just go away on its own. So this graph has all three symmetries. Any idea what the shape of this graph is? Circle. So visually, if you take a circle that is centered around the origin, and if you fold the graph across the y-axis, there's perfect symmetry here. The two sides will overlap each other. If I were to take this circle and fold it across the x-axis, I also get symmetry. And if I were to flip this circle upside down, it will be exactly the same graph. Okay, so all three symmetries exist for this graph.
Are there any other graphs where all three symmetries exist?
I believe it's only circles. Square. Yeah, but there's no equation that's going to give us a square unless we do piecewise. So yeah, I think equations that are where we can, that is standalone, where we're not piecing together different functions. I think circles is the only one I can think of.
Okay, thank you.
Yeah. All right, next page. All right, points of intersection. So to find this, basically, if we want to find where two graphs intersect each other, we can solve an equation for one variable and substitute into the other equation. Okay, so find the points of intersection for the following. X squared plus y squared equals 25, and 2x plus y equals 10. Okay, let's visualize this. What is the shape of the first equation? Okay, I'll put this to the side here. And then 2x plus y equals 10 is a what? The line. Let's just go through some visual possibilities here. What's an example? How many points of intersection could we possibly have between the circle and the line?
2.
2. Okay. If you have a circle and a line that goes through it, we can visualize and convince ourselves it's possible to have two solutions. What's another possibility?
I don't have any.
No, that's right. No solution. If the line never touches the circle, then there will be no solution. And there's one more.
You have one.
Yeah. So if you have a line that grazes the surface of the circle at just one point, we call that tangent to the circle. There will be one solution, right? So there's three possibilities. There's two solutions possible. Right? It's possible that we get zero solutions. It's possible we only get one solution. Right? We're gonna discover which of these options we're dealing with algebraically. Okay, we're not gonna graph this per se. We're just gonna see if we can follow these directions and discover what the intersections is and also how many there are. Okay, so we're gonna go through substitution here. So substitution is where we try to take the path of least resistance. We're trying to find the variable that's the easiest to get by itself. So between these two equations and the variables that you see, which variable would be the easiest to isolate? The y, right? The x squared, we can isolate all the other variables, but it's just messier, right? If I want to get that x by itself, I gotta subtract, I gotta do the square root. Same thing here. I mean, the 2x is okay, but I gotta deal with a fraction because I gotta divide everything by 2. The y is the easiest to get by itself. So it's not wrong to pick other variables, but we typically want to choose the easiest path. So if I want to solve for y is equal to 10 minus 2x. I'm simply subtracting that 2x over to the right side. And I'm going to try to use this and work with the other equation. I know that y is 10 minus 2x. I'm going to use this to substitute into my other equation. And the reason why we want to do that is because right now, as it stands, we really can't solve for either equation because both equations, there are too many variables, right? We want to get both equations down to, or want to try to at least get one equation down to one variable. If I can do that, then I have a much easier time solving one variable at a time. So I know that y is equal to 10 minus 2x, so I'm gonna simply replace y with 10 minus 2x. So that means I need to put the 10 minus 2x in a set of parentheses because all this needs to be squared. So we're making progress because we're able to get this equation, one of the equations, down to one variable. And we still have quite a bit of work ahead of us because things are not cleaned up just yet. Okay, now how do I resolve this set of this parentheses here? Can I just distribute the square through? Well, right. So as a reminder, we have to take the time to distribute these terms through each other. The temptation is, I see some students do this, where they distribute the square through, and they just make it 100 minus 4x squared, okay? If we do that, we have part of it, but we don't have the whole thing. So the easiest way to see it clearly, let's write out both sets of parentheses and convince ourselves that we're hitting every term that needs to be hit. So we'll take the time, distribute each term through each other. So I'm going to distribute the 10 through, distribute the negative 2x through. Let's get rid of all the parentheses, and then we can work on combining like terms. Okay, let's combine some like terms. We can also try to get everything over to one side of the equation, force a 0 on the other side. 1x squared plus 4x squared is 5x squared. You've got these middle terms here that you can combine. And I can merge the 125 together, but I do need them on the same side. I'll subtract the 25 over to the left side, 100 minus 25. Any questions here? All right, we do want to factor, but before we do the trinomial factoring, what can we do first?
Less than 5.
Good, GCF. So we'll deal with the GCF first, and then we can worry about the trinomial factoring. So every term can be divided by 5. So I will divide a 5 out, which is my GCF. All right, so now I'm going to focus my attention on just the parentheses. You guys probably learned factoring in a lot of different ways, depending on how you were taught. But I can go through a star method here. Multiplies to be the last number, adds up to be the middle number. So multiplies to be 15, adds up to be -8. It's a little puzzle here. -5 and -3, right? -5 and -3 is 15. -5 minus 3 is -8. So we know those two numbers work. So once we find the two numbers that will allow this to factor nicely, we're going to get that trinomial in factored form. And we're going to solve for x. Okay, so what are we expecting here? How many intersections here? 2, right? Okay. Now that 5, this 5 is not going to mean anything for us because if we try to set that 5 equal to 0, it's not going to make any sense. So we can just basically ignore the 5, just focus on the x's. Okay, so we have 2 points of intersection, but we're not quite done yet. It's asking for points, so what else do we need?
The Y.
Good, we also need the y value. Okay, now how can I find the y value? Yeah, does it matter which one I plug into? No, right? Because either graph, they're both intersecting at the same point, so it doesn't matter which one, but we typically want to choose the easier one to plug into, right? You can either choose one of these original ones, or you can choose the second one that's already kind of built for us solving for the y. So I'm just going to insert into that y equals 10 minus 2x, but any of the three will do. Ten minus 10 is 0. 10 minus 6 is 4. So you're going to represent your ordered pairs. Represent your answer in ordered pair form. 5, 0, and 3, 4. No, you don't have to. You can still comma. That's fine.
Just write our answer like that, like it doesn't need to be anything equals.
No.
Okay.
Yeah. Okay, any questions? Okay, so example 3 is reviewing or practicing the concept we learned on the first page. So see if you can try this on your own. Find the x and y intercepts. So the way we find x-intercept, go ahead and replace your y with 0 and solve for x. To find your y-intercept, replace your x with 0 and solve for y. Okay, so the hint is that we're not guaranteed to find x and y-intercept for every graph, right? Some graphs may not have one versus the other. Or sometimes the graph would have both. It just depends on what we find. And also, we're going to determine the symmetry. So determine the symmetry algebraically. So see if you can test one of the, or test the 3 possibilities on the previous page and determine, can I replace the x with negative x and get back to my starting point? Can I replace y with negative y, get back to my starting point? Place both the x and y with negative x and negative y, get to my starting point. And if I can, then that will be the one that has symmetry. Okay, so it's possible to have either one of those 3 symmetries, all 3 symmetries, or none. So there's potentially 5 different options for dealing with symmetries here. Okay, so spend a minute, try that, and I'll go over it in a minute. Careful. It's for fun. It's for root. Yes, they are perfect. That minus those y squared equals 25, x squared minus. Yeah. Yeah, so this tells us that as an imaginary number, we're not covering that in our course, so that would consider the does not exist. It's valid distance. So that's right. So we would have to mess this up. No, it wouldn't mess it up. It just means that the graph doesn't have the x, doesn't have the y-intercept, but it can still have x. And I'll show you by graphing it for you. Thank you. Okay, so let me ask you guys this. Is there an x-intercept?
Yes,
Okay. Is there a y-intercept?
no,
No. Okay, I'll show that. I'll go through the work in a second, why there is not a y-intercept. And then is there symmetry? Which symmetry do we have?
X-axis?
X-axis. Okay, so let me go through each of those points, make sure you don't have any questions. So for x intercept, I'll take the y, replace with 0, and see if I can solve for x. Once I replace that y with 0, I get 0 plus 1, x equals 1. That's a real number. We're good. X-intercept is at 1, 0. Y-intercept, take the x, replace with 0. But we're going to run into an issue here because if I try to get y squared by itself, I get y squared equals -1. And we know that when we take the square roots of a negative number, that falls under imaginary number category. And we're dealing with a real number system. So for us, that would be considered does not exist. And so that's why there is no y-intercept. Okay. What kind of tips us off as to which one has which symmetry it has? I'm looking at that y squared, right? Because I know that if I replace that y with negative y, it'll go away cleanly for us because that square will just take care of it. So because I'm able to replace y with negative y and convince myself that I can get back to my starting equation, I know that must be x-axis symmetry. So I want to kind of show you what this graph looks like to show you or to convince you that these algebraic steps matches what we can see visually. So this is a parabola that is opening sideways, and it has an x-intercept at 1. So it's going to look like this. Notice that because the graph is opening to the right of the y-axis, it's never going to touch the y-axis, and therefore that is why there is no y-intercept. You can visually see that this is x-axis symmetry because this is not a function, but we can visualize how this graph can fold over the x-axis and achieve overlapping symmetry. All right, so we have about 15 minutes. I would like for us to get started with the P1 assignment. So if you can turn to page 11. And the assignment is 19 through 25 odd, 57, 59, 61, and 62. Oh, so that's 19, 21, 23, 25. Yeah, it's odd number. So it's all there for you. Now, if you don't have loose leaf paper or don't have a notebook, you need to come up and grab loose leaf paper here. I have printer paper here as well. But even if you don't finish your assignments, once you get started, I'm not going to check until next Monday, but I'm going to give you time each day to at least get started to get the practice that I want you to have, but then also so that you're I'm not waiting till last minute to do these homework. Oh, and then sorry for the calendar. I think I didn't check that I didn't name each of the days here, so it's Monday, Tuesday, Wednesday, Thursday, Friday at the top. Yeah. Yeah, go ahead. Guys, if you need to use the restroom, you can just grab any of the hallway tabs that's hanging near the lights there. No, let me sign up. Just grab one. That's right. Yeah, just those three. Just those two. after a few minutes, I'll put up each of the problems that you guys are starting with, so you guys can double check. But if you're working ahead, you can also go to the very back of the packet and check your answers. So 19, you're going to get 2 x-intercepts and 1 y-intercept. Yeah. Okay. You good? Or you want to show me?
Don't show me, please.
Okay, so x squared plus x minus 2. So multiplies to be,
I got it.
you get, all right.
Thank you.
Everybody good with 19? Okay, 21, y-intercept is manageable. X-intercept seems a little bit strange here because you got to go with the square root. But just think of the square root as completely separate from the x. So really, we're ready to set each equal to 0 separately. Because these are being multiplied and you got that 0 showing up, I can set x equal to 0. That's one intersection. And I can also set the square root 16 minus x squared equal to 0 and deal with that separately. Okay. Now, something that some of you guys brought up here, we got to be careful how we handle this problem. Even though square root of 16 is 4 and square root of x squared is x, you can't quite do this. Can't quite do that because there's a minus sign here. So anytime there's addition or subtraction, it kind of messes things that we would normally like to do. Now, if it was square root of 16x squared, then that's fine. I can take the square root of 16, square root of x squared is x, and that's fine. But when that minus is in the expression, we can't make this jump. Can't do that. So the way around it is we want to get rid of both. We want to get rid of that square root. If I square both sides, then the square root goes away and I can solve for x.
get that, 16 minus x squared. Yeah.
So the x and the square roots, these are being multiplied, so I can treat them like separate entities. So it's kind of like this. It's kind of like the previous problem, where if I had x plus 2, x minus 1 equal to 0, these are completely separate, so I can set both equal to 0 apart from each other.
Okay.
So I can do that here as well. Because these are being multiplied, and also because there's a 0 that allows me to do that on the other side. Now, once you get to your x values, you still need to find what? Y's. That means we're going to insert back into the either equation, right? So in this case, we're going to get 3 intersections. Or sorry, 3 x-intercepts for this bracket.
Where did you get 0, 0 from?
How to get 0, 0? Well, I'm doing y-intercepts. So to do y-intercepts, I replace every x.
Here.
And then 0 times root 16. That's root 4, but anything times 0 is 0. So that's forcing me to return a value of 0.
So then it'd just be a wash.
Yes, that's right. Yeah. So 0, 0 is x-intercept and a y-intercept. The intersection of both the axes, so it's going to show up in both spots. Yeah. Guys, 5 minutes remain before the bell, so you guys are welcome to come up and grab your phone. Yeah, so I'll do it here. X squared plus x minus 2. Okay, so we ask ourselves, what multiplies to be a times c and what adds up to be b? So a times c is 1 times -2, which is -2. My b is 1.
Wait, why didn't it, well, the x squared turns into 1, right?
Yeah, so my a is 1, my b is 1, and my c is.
Oh, okay.
So it's gonna end up being 2 and -1. 2 times -1 is -2. 2 minus 1 is 1. So those are the two numbers that's gonna go in that bracket.
No, what happens to the x squared, like, why is it?
Because it's in factor form, so I'm able to break that x squared back to x's. Now, if I want to convince myself that these are the same, I can FOIL this out, and that will take me back to the sign.